This video is on phase diagrams. A phase diagram represents phases of a substance in a closed system as a function of both the temperature and the pressure. There are a couple different points to a phase diagram. Notice that a phase diagram has three distinct sections, and our labels of our axes we have on our y-axis we have pressure, usually in atmospheres, but that could be in torr, millimeters of mercury, or kilopascals. And then our temperature is usually in degrees Celsius, but it could be in Kelvin. We'll notice that our first section here is our solid. This is at low temperatures and any range of pressure. We know that at very low temperatures, we have slow movement of our molecules, so it makes sense that this would be in the solid phase. At very low pressures and low temperatures, we can be in the gas phase, so that's why this area here exists. A gas phase can be any range of temperatures and then really any range of pressures until we get to this point here, which is our critical point, which we'll talk about more in a second. In the middle here, I have my liquid phase. So liquid phase has medium kinetic energy moving molecules, and they're going to have a medium number of collisions. So here, I'm at a mid-range temperature and mid-range pressures. These lines represent equilibrium. On the line, we're going to have both phases present at equilibrium. So anywhere on this line, we have both solid and liquid phases present. Here, solid and gas. Here, liquid and gas. As we cross the lines, we go through phase changes. So I can be at one continuous pressure and cross the line here, and I would go from solid to liquid, so I'd be melting. I could also be at one distinct temperature and go down by dropping pressure and cross my line. And again, I'd be going from solid to liquid, so I would also be melting. Liquid to gas is sublimation. Gas to solid is deposition. Liquid to gas is evaporation. Gas to liquid, condensation. We have a couple of unique points. Here where all three lines intersect is called the triple point. Here's the temperature and pressure where all three phases coexist at equilibrium. So at this exact point, I have solid, liquid, and gas phases occurring simultaneously. Here we have something called the critical point. This is a temperature and pressure where you can no longer have a liquid. The difference between liquid and solid kind of gets fuzzy at this point. So at the critical point, we have both a critical temperature and critical pressure. The critical temperature is the temperature above which the vapor can no longer be liquefied no matter the pressure. So above this temperature, I cannot make a liquid. The critical pressure is the pressure required to produce liquefaction of a substance at the critical temperature. So at this point, the distinction between liquid and gas isn't really easy to define. We say that's kind of a fluid state. So let's look at the phase diagram of water. We'll notice something different right off the bat. So the first thing we notice about our phase diagram of water is our line between our solid and our liquid phase has a negative slope. This is because the liquid is denser than the solid. The liquid is favored at higher pressures. Notice at higher pressures, the liquid phase is favored. And we'll notice that the melting point decreases as pressure increases. So as I go up in pressure, my melting point decreases or goes back. So we'll notice that on my chart here, it's definitely not drawn to scale. And I have some different pressures along here. I have things in torr. This is 455 or 4.58 torr as well. Atmospheres and 225 atmospheres. Okay. We have four different lines here. We have X1, X2, X3, and X4, and these are different experiments. We're going to talk about what happens. So notice that all of these we have steady pressures, and we're going to increase the temperature at these. So my first one, X equals 1, I'm at 1 atmosphere, which we know is our normal atmospheric pressure. I'm going to slowly increase my temperature. So I'm starting down at negative degrees Celsius, and I'm going from a solid to a liquid to gas. So I'm going from a solid to a liquid to a gas. we're also going to talk about vapor pressure, which is something we haven't talked about with phase diagrams before. Vapor pressure exists in solids, liquids, and gases. However, something does not boil until the vapor pressure and the external pressure are equal. So evaporation along this line here is where the vapor pressure and the external pressure are equal. So make a note that along this line, the vapor pressure equals my external pressure. So this is why we can have a flask and we can hook it up to a vacuum pump and decrease the pressure, and we can make the water in our Erlenmeyer or our sidearm flask boil without increasing the temperature, just by simply decreasing the pressure. So if you haven't seen this, you can look it up on YouTube. Just look up boiling water by decreasing pressure, and you should be able to see some videos of that happening. So here, both my solid and liquid have a vapor pressure less than 1 atmosphere. So in here, vapor pressure less than 1 atmosphere. Until I get to 100 degrees Celsius. At 100 degrees Celsius, my vapor pressure now equals my external pressure, and evaporation can occur. At x equals 2, I'm starting at 2 torr. I'm going from a solid to a gas. It's at extremely low external pressure, only 2 torr. So while my substance is a solid, it has a vapor pressure of less than 2 torr. So these are the vapor molecules inside my solid, or the vapor molecules inside my liquid. Not necessarily the ones right at the surface, because again, this is a closed system. So my vapor pressure of my solid ice is less than 2 torr until I get to this negative 10 degrees Celsius. At negative 10 degrees Celsius, my vapor pressure of my solid is equal to my external pressure. So it equals 2 torr. And therefore, because now my vapor pressure equals my external pressure, evaporation can occur. And now I'm at a gas or a vapor. X equals 3 goes through my triple point. For water, that's at 4.58 torr. Prior to getting to my triple point, my solid is at a vapor pressure less than 4.58 torr. Once I get here, both my solid vapor pressure and my liquid vapor pressure here at this point equal 4.58 torr, which is why sublimation and evaporation occur, and I'm able to have all 3 phases coexist. Finally, at x equals 4, which is at 225 atmospheres, so this is super high pressure, I go along and my vapor pressure does not really ever equal my external pressure, so it doesn't really ever become a gas because I'm past my critical point. When I'm past my critical point, we say this is our fluid region, and in our fluid region, you can't really distinguish between both a liquid and a gas. So this leads us to the question of why do we glide on the ice when we ice skate? Well, when we glide on the ice, when you're wearing an ice skate and your ice skate is on top of the ice and you're standing on it, you exert pressure on the ice. So if I have a solid and I'm exerting pressure, so I'm increasing the pressure. So let's say I'm here at atmospheric pressure. So at 1 atmosphere. And it's cold out, right? It has to be below 0. So I'm somewhere over here at 1 atmosphere. Now, I have weight and mass. So I step on the ice, and that's going to increase the pressure on the ice until I increase the pressure on the ice that is equal to the vapor pressure, not the vapor pressure, is equal to the pressure at which my solid will turn to a liquid, and I will get my liquid to melt. So I skate, increase the pressure on the ice, that briefly melts the ice and then allows us to glide across the ice. And then after I'm done gliding across the ice, my skate leaves, so my pressure decreases, and then it goes back into my solid phase.